Okay, now I'm going to talk about Class A and Class B amplifier. So the difference between Class A and Class B, what are the difference? So I've rearranged this thing, okay, from the tutorial. As you can see, okay, so we have a gain of 5, okay, the amplifier has a gain of 5, and then so we have a signals going through a Class A amplifier and a Class B amplifier containing MPN and PNP. Actually, Class A contains only MPN, I think, and then for Class B contains both MPN and PNP. Okay, so if you have a signal that is this one, okay, these are all the signals, but take note that they are actually the same amplitude. Okay, they're actually the same amplitude, just that they are being they have a bias voltage put across. What do I mean by bias voltage? So as you can see, this is the sine X graph, right? If I were to input, if I add in a let's say 3, you can see that I actually am like bring it upward, right? You know, if I bring it down, or maybe I revert, if I minus, like maybe -4, -3, -2, -1, yeah, whatsoever. So as you can see, these are the things. So this dude over here affects how the sine X graph is being oriented in a voltage time graph in a sense. Okay, so the voltage time graph in this sense is actually what we are being shown over here. So these are the voltage in the y and the time in the x-axis. So the biasing voltage is this one. Okay, you have another source coming from another place trying to bring this thing up. As you can see, in this case there is no biasing voltage, right? Start from 0. However, you have a biasing voltage of like 0.25 in this case, right? You bring up the thing, but the amplitude are all the same, right? They are all the same from like 1.75 to 0.25. So 1.75 minus 0. Okay, this one is 0.75, sorry. So 1.75 minus 0.75 is still 1, right? So this one amplitude is the same thing over here, right? So in other words, this is 1.75, this is 0.75. If you minus, you get a 1, right? Same as this thing. So I didn't change the amplitude at all, okay? I didn't change. I simply putting in a biasing voltage over here, you know? So in this case, I put in a biasing voltage of 0.25, 0.75, sorry. And then for this case, I put in a biasing voltage of 1, right? Okay. So I start from 1. This one I start from 0.75. This one I start from 0. So this experiment wants to exhibit that the larger the biasing voltage, the lesser your distortion. Okay, as you can see, the lesser your distortion. So for this, in this case, there is no biasing voltage. Okay, so maybe this is 1 volt. So in this case, there is no biasing voltage. This is actually class A lah. Okay, so you can see that there is so much of a distortion. Okay. However, one good thing for class A is that you are bringing all the you can see that this thing over here is being rectified. It's being brought up over here into the positive side, right? So this thing is being moved up here. So at least you have a certain amount of voltage lah. Although there is no voltages. Okay, but I mean, yeah, whatever. At least you're bringing it up to the positive side lah. That's all. Although not positive, but rather than because if you have this current, you have in the end, if you integrate or whatever, you get 0 because this one will cancel out this one, right? So you will have nothing as an output, I guess. Yeah. So if you have this class A, at least you have this thing to account for. You have a certain amount of input in this case. That is what it means lah. Okay, so if your biasing voltage is is 0, your distortion is at least you bring it up to this. At least you have certain output already. If you were to further increase the biasing voltage, you can actually increase your amount of output. In this case, you have more output, right? Because your output is hold on, you have more area under the graph lah. Okay, as you can see, this one, if you were to take a look, this portion over here, maybe I should draw in a red color. This portion over here is the same as this thing, right? It's the same as this dude over here. So if you were to have a 0.75 volt like biasing voltage, you can actually amplify this one also, right? You actually amplifies this one. You can actually have additional one. As you can see, these are all positive now. They are all at the positive side. You see, they are all above the 0 voltage. So they are all applicable for usage in this case. Okay, and then as you can see, if you were to further increase the biasing voltage, you can see that you have a more surface to more. You have a you have a more what, less distortion. Okay, you have less distortion. Okay, because you want your output to be the same as this one, right? So in this case, you can see that it's exactly the same now. So hopefully this gives you a clear idea of class A. Okay, so what about class B? So in both cases okay, in both cases, class A and B, the higher the biasing voltage, the better it is lah. You have lesser distortion, as you can see. This direction is increasing biasing voltage. As you can see, there is distortion over here, there is distortion over here, and lesser distortion over here, right? So when the more you increase your biasing voltage, the more you have lesser distortion. That's all we say. So for class B is a different case. Class B, for class A is only using one transistor or one NPN or maybe PNP lah. Either one, okay. But for this case, class B is both. Okay, they are using both. But nonetheless, I may be wrong. Maybe this is only NPN, but whatsoever. But in this case, class B is only it's using both NPN and PNP. So this signal uses NPN, while this signal uses PNP. So this side operates in the negative area. This side operates in the NPN area. So in this case, they're operating in a different zone. Okay, and then this dude is working on this side. So if you were to rearrange them in the machine, you can actually flip this dude up over here, so you can have a signal like this. So you have a good signal, whatever. So you have more signals over here, right? So this is exactly what class B is doing lah. Okay, so NPN is working on one side, PNP is working on the other side, and then you flip it out, and then you can have a full voltage usage, which is like a bit in bar. But nonetheless, as you can see, the distortion here is not very big. Okay, the distortion here is just like minority compared to this one. Okay, so as this is why it also says that what, this is efficient. Okay, this is efficient. Why efficient? I mean, this is class B also. Yeah, so this is efficient. Why? I mean, this is efficient. Why? Because as you can see, comparatively, right? When you have zero biasing voltage, okay, when you have zero biasing voltage, the class A can only output this amount. However, for class B, you can see that it outputs so much. You can output all these signals throughout. You can output all these signals. You see, just that there's a little distortion. That's all. So comparatively, class B is more efficient than class A. But however, at a higher biasing voltage scenario, um yeah, I forget what I'm talking about, but anyway, so the good thing for class A is that when you have a higher biasing voltage, okay, higher biasing voltage, you have no distortion. Your signal is very nice. Okay, if you have like maybe 30 volts, your signal will be exactly like this. Okay, or however, you have a 30 volts over here, your signal might not be as nice as class B lah. I mean class A lah. I think only lah, but because from my notes it says that class B may still have a certain distortion compared to class A. Because but however class A is less, it's not efficient. Why class A is less efficient than class B? It's mainly because P equals to VI, right? Because for MPN, for class B scenario, you can actually no need additional biasing voltage. Okay, you don't care if you have this one. It's all the way this one. You just have a little notch over here. That's all, right? This notches. It's just a little bit distortion, but you don't need a biasing voltage. But however, if you have a class A, in this case, you have a biasing voltage. V times whatever input current, you have a more power. So if you on your computer for on like long time, like ensuring that all the signals are being amplified in such a nice curve, you know, your amount of power consumed will be very big. So you're gonna pay more, okay? You're gonna pay more. So class A is less efficient than class B. So there is a thing or two in this thing. Before I go, I'll just give you an intuition that wow, there is also A, B, class C, class D, whatever. So just to let you know that class A, B, you have this type of curve. Okay. So what is it? So class A, B have both rows of A and B. Okay, so these two are actually class B, right? Because class B have MPN and PNP both things. So each operating in one part of the signal. However, as you know, there will be a distortion over here, right? So class A itself comes in. So the class A amplifier comes in order to solve this thing. However, you have 78.5% of the you'll be less you have like lesser accuracy, but however better than class B lah. Okay, so class A B has a has a thing for class A and B, whatever. So just to let you know lah. And then class C, what is class C? Class C is conduct less than 50%. Okay, so when you have a 100% signal, when you come out, you only have like like that only. But however, your efficiency is very high because you're gonna increase this thing into such a high amplitude. Okay, which is pretty good. But application wise, I don't know. You actually can read it up over here. But these are all the value-added things may like trick question test may come out. And then class D is like whoa, I don't know, another level. Class E, whoa, capacitor, and then G and H, which is like wow, I don't know what the hell. So these are the things you may want to take a look. So I'll see you in the next video for like other stuffs. So see you there.